Welcome to the most difficult chapter. So this chapter, in my opinion, this is the most difficult chapter because it's really calculus based. And calculus is not a prereq for this class, but it's still there. We teach it in terms of algebra, but you're really being taught calculus. So this is the mathematically most difficult chapter. So you might have to, this is the one that's going to be pretty tough for most students. And it's about the kinetics. So it's how fast things are going, and really what the kinetics are, it's the derivative, and we'll talk about that. But how fast are things going? Like, well, let's say you have a scorpion or a lizard and you want to catch them. What's the way you could do it? I do this if I ever find a gecko in my shower. This is what I do. I pour cold water on it. And I grab the gecko, and then I can scurry it outside. They do this with scorpions too. Like I've seen it on TV shows. They put scorpions in coolers and they place them on people, and the scorpions are too slow to sting you. And you can slow them down. You can by temperature. So temperature is an issue with chemical reactions. We'll talk more about that later. And we're going to talk about the kinetics is the rate of reaction. And the rate of reaction is the change in concentration over the change in time. That's akin to speed, right? So speed is the change in distance or displacement over time, over the change in time. So like miles per hour. So if you're going 60 miles an hour, that means in a time change of 1 hour, you will go a distance change of 60 miles, for instance. So in these brackets, you can see brackets, these means moles per liter. So, for instance, let's look at this chemical reaction here. H2 plus I2 makes 2HI. And the rate is, you can look at the view of the rate as the change in concentration. And the capital delta there means change. Change in concentration of hydrogen over change in time. So the delta bracket H2 over delta T. That's delta T. T is time. You can look at that as at the hydrogen concentration at time 2 minus the hydrogen concentration at time 1 divided by the distance in the time, or the difference in the time. That, if you carry that on to infinity, that is one of the definitions of a derivative. And also final, change is always final minus initial whenever you see that. So, and from this equation here, so the rate of disappearance of hydrogen is equal to the rate of disappearance of iodine. So that's where this equation comes in. So the rate, and it's going away, so it's disappearance. The rate of disappearance of hydrogen is equal to the rate of disappearance of iodine is equal to 2 times the rate of appearance of hydrogen iodide. Why? Because there's a 2 there, the stoichiometric ratio. So let's do this. Let's look at this example. We have hydrogen peroxide plus 3 iodides plus 2 hydrogen ions makes I3 minus plus 2 waters. In the first 10 seconds of reaction, the iodide concentration dropped from 1 molar to 0.868 molar. So what is the average rate of this reaction in the time interval? So to look at this, we have to do the final minus the initial. So final, so for I minus, so the change in I minus concentration over change in time. If you look at this, so compare it to the entire reaction. So iodide has a factor of 3 here. So the reaction rate for the entire reaction is going to be 1/3 of that, because there's a 3 here. For every unit this reaction is going forward, iodide is going at 3 times that rate. So you have to put a 1/3 there. In which direction is it going? So the reaction rate is going forward. Iodide is disappearing, so put a minus there for the disappearance of the iodide. And then we have to do the change, final minus initial. So 1/3 minus 1/3 times the concentration change. So final is 1. No, I'm sorry, the final is 0.868 minus 1. So that's the change in concentration. Change of time is 10 seconds. And putting it all together, you get 0.0044 molars per second. So this means that this whole reaction, this entire reaction, is going forward at a rate of 0.0044 molars per second. So then predict the rate of change in the concentration of hydrogen ion. So for part B here, there's a 2 there, so it's just going to be minus 2 times the rate. And why is there a minus? Well, the reactants, these are all negative. The products are all positive. The reactants go away, they're consumed. The products are formed, they're positive. So minus 2 times the rate, this is 0.0088 molars per second. So that's, oh, and it's a minus, sorry, I forgot the minus. So it's the change in concentration of hydrogen ion is minus 0.0088 molars per second. So let's see if we can do this. This is designed to be an easy one. Blood glucose levels drop from 120 to 110 milligram per cubic millimeters in an hour. What's the rate of disappearance of glucose? And it's going to be going away. Okay, so rate laws. We're going to talk about rate laws. And right now, where we are at with our understanding of chemistry, we can only experimentally determine rate laws. So rate laws are not something we can determine by using computer simulations or other things. We're getting better, but we're just not there. It's really only experimentally determined. And so our rate law, we have reactant A going to products. And then the rate of this reaction, we have reactant A. This rate is equal to the sum rate constant, which turns out to be temperature dependent, concentration of A raised to some power. And that power that the concentration of A is raised to, that is known as the reaction order. So that's one reactant. What about 2? What about 2 reactants? We have A plus B goes to products. Then the rate law is going to be rate is equal to some constant, the rate constant, times the concentration of A raised to some power, concentration of B raised to some power. They could be, and in this case I put N and M. They can be the same, they can be different. I guess my Apple Pencil's going down. I'll fix that. So, but anyways, so next thing we're going to do is talk about these coefficients, these exponents N and M, how we can determine them. So reaction order is the first one. Let's do the easiest. The reaction order is 0 order. That means that the reaction concentration has absolutely no effect on the rate. The rate is equal to just some rate constant. So for instance, a physical process like sublimation. Sublimation turns out to be 0 order. So on the graphic on the right, it doesn't matter what the concentration is. The reaction, or in this case the process, goes forward at the same rate. It has no effect. Second thing we'll talk about is first order. So first order rate is equal to the rate constant raised to power of 1. And this is what most things are. Almost everything is first order. And only that, we can make anything first order if we want to. So that's called pseudo first order. So, well, first order, double the concentration, you double the rate. Or you half the concentration, you half the rate. So that's first order. And almost everything is. Nuclear decay, first order. Interest in banks, first order. Almost every chemical reaction is first order. So, but then chemistry, and we do see things there, second order. Rate is equal to some rate constant times the concentration A to the second power. In this case, if you double the concentration, you quadruple the rate. So this second order can go away. You can also have fractional rates as well. Now for multiple components, your rate is equal to the rate constant, concentration of some reactant to some power, concentration of the other reactant to some power, so in this case A to the N, B to the M. The overall reaction order is the sum of the two exponents. If there's three things, then it's the sum of three exponents, but typically you don't have three things colliding at the same time. It's usually only 2-point collisions happen. Okay, so let's look at some of these. So if you look at the y-axis, it says concentration of reactant A, x-axis time. As time is moving forward, a zero order, the concentration just goes down a straight line. First order, it's a parabola. Second order, it's a cubic, so going down that way. And then the rate versus the concentration, so it's actually the derivative. So for a zero order, the derivative of a line is a constant, so that's a constant there. So if you don't understand the calculus, that's okay. The derivative of a parabola is a straight line, so the rate versus concentration is a straight line for first order, and it's a parabola for second order. And how do you determine a reaction order? So this is the way you do. I'll just show you do it a more mathematically rigorous way later, but this is how you can determine it via a process called inspection. So how do you determine reaction order? Rate, again, a rate law is equal to, and I'm sticking to the simplest one, rate is equal to some rate constant, concentration of A raised to some power. If it's first order, if you double the rate, so this one illustrates first order. If the rate is doubled, so it goes from, if the concentration is doubled, so A, the concentration doubles from 0.1 to 0.2, what happens to the rate? The rate doubles. That shows that the first order happens. So, and here is a proof as well, if you want to go through something a little bit more rigorous. Zero order is easy to find. The rate has nothing to do with the concentration, so that's zero order. So zero order is easy. And then, so second is second order. If you double the concentration, the rate goes up by a factor of 4. So, and then here's the proof for that right there. All right, so let's apply this for a problem. So rate right here. So we have some equation. So concentration of NO2 plus CO makes NO and CO2. So the rate is going to be equal to some rate constant, concentration of one reactant raised to some power, concentration of the other reactant raised to some power. And that's, so right there, this is considered to be chemistry common sense. So you should be able to look at this and pick the reactants and say, okay, there's going to be some exponent, and then place them in like such. All right, so we can solve this two ways. So the first thing we got to do is figure out what N and M are. So the overall rate equation, rate law for the equation, and then the rate constant. So you can start by doing what's called inspection. Notice the carbon monoxide stays the same. This one goes up by a factor of 2, and this one here goes up by a factor of 4. This means that N equals 2. And also, if you look, I'll change the color. This one goes up by a factor of 2. This one stays the same. And then this one doesn't change. This means that M is 0. So you can do it that way. That is one way to solve this. Let's say that you didn't do the inspection and you want to solve it mathematically. What you do is you take this rate law and you apply it. So I'm going to look at the rate. So I'm reading the rate here. So rate is 0.0021 equals my rate constant times the concentration of NO 0.1 to the N carbon monoxide 0.1 to the M. Now, actually it makes sense to put this on the bottom. I'm going to move this one down. Now I'm going to write a second time with a different color this line. So our rate 0.0082 equals a rate constant, concentration 0.2 to the n 0.1 to the m. Actually, maybe I'll get a little more space here. Move this up. I'll move the decimal point. And now what are we going to do? We're going to divide these two equations. So I'm just going to divide them, and notice a couple things, that these cancel, and what we are left with is 0.0082 over 0.0021 equals 0.2 to the n, 0.1 to the n. So I can further simplify this. 82 over 21 is, so these are the same ones, so you have 0.2 over 0.1 to the n equals 2 to the n. So now how do you solve this? 82 over 21 equals 2 to the n. You can take the natural log of both sides. ln 82 over 21 equals n ln of 2. And this is one of those rules. So if you have natural log of the quantity x to the a, this equals a ln x. So this is just a math definition. So this means then our n is equal to the natural log of 82 over 21 all over the natural log of 2, and that's what that is there. So that this is equal to 2. So that's the way you do it, doing the long way mathematically. So first part, what's the rate law? And we've said that before. It's zero order. It's second order for NO2, but it's zero order for CO. So the rate law is equal to the rate constant times the concentration of NO2 squared. Okay, so now the next thing we got to do is get the rate constant. Now that we have the rate law, all you got to do is plug in the numbers. So this rate equals k NO2 squared, so I'm going to put in the rate, 0.0021 molars per second equals a rate constant times concentration of NO, 0.1 molar squared. And now we solve for k. K equals 0.0021 molar per second all over 0.1 molar squared, which equals 0.0021 molar per second. 0.1 molar squared, this is 0.01 molar squared. So this equals 0.21 1 over molar second. So then typically though when we write this, we write the K as 0.21 molar minus 1 second minus 1. I don't know why we write it this way. I think it's because of typewriters. It's easier to write it this way with a typewriter rather than in an equation format. Although it is proper. That's proper to do it that way. So, but it's one of the strange things we do. Okay, so this means that the whole rate law then, if we want to be the big, like write everything out, the rate law is equal to 0.21 molar minus 1 second minus 1 concentration of NO2 squared. So here is our big ending like that. Okay, so recap with this one. You can use inspection or mathematics. So rate doubles, then the concentration doubles here, rate quadruples here. This means that the NO2 is second order. This doubles that, and the rate stays the same. Therefore, it's zero order with carbon monoxide. So we can then write out the rate law this way, and then we can plug in the rate law to figure out what the rate constant is. You can pick any of these for the rate constant. I like this one because it's in 0.1s. It's easy for me to do the math in my head with the factors of 10. So you can pick any one you want. They're all the same answer. Okay, so let's see if you can do this one. Give it a try. And so go ahead and pause and work on it. But the rate law here, and I try to be a little sneaky because actually this is the fractional rate law. So the answer is D. And you can do it by inspection though, like that doubles, that's first order. That goes up by a factor of 1.42. That's close to square root of 2. So 1.414. So I remember that because square root of 2 over 2 in geometry for the 45-degree triangle, it says radical 2 over 2, 40, it's square root of 2. That's 0.707. So 1.414 is just the square root of 2. That's how I remember it. So you can do it by inspection, or you can do the long way if you want. That's how you do the long way. And then there's the rate constant if you keep on going. So in the classroom, of course, I spend a lot of time going over this, but you are not in my classroom. You are online. So, but hopefully you can try this out on your own to get a similar experience.